I will talk about performance optimizations and especially useless ones. And I'm a bit surprised that I couldn't scare away more people with this title. So you are probably very enthusiastic to hear about this, and I hope I won't let you down. Despite the fact that in this talk we will go down indeed, very, very deep down, below the Erlang layer and core Erlang, and we will investigate the lowermost programmable layer on the BEAM, its assembly language, and see what kind of performance tricks can we pull when we go there. And if your first question is why would you even consider doing this? Because yeah, normally the assembly layer is something that's an internal thing between the compiler and the VM, isn't it? You don't really think about it. I'm totally with you. But I can give you a few examples when this normally hidden layer just popped up its head and bit me. First example is about the ref trick. I hope everybody have at least heard about the ref trick. Before, this is a very nice optimization the compiler can do with your messaging code. And on the left-hand side, you can see the textbook implementation. This is textbook case. This is the do call function from the gen module that's powering all the gen behaviors in OTP. The trick is in the receive statement, and all the clauses pattern match on mref, which the compiler knows that is because it's in the first line of the function, is a fresh, unique value of a reference that couldn't exist on the machine at all before we called Erlang monitor. So it knows that none of the messages that were in the process's mailbox at that point could match. It can skip the expensive pattern matching for those messages and start from the then end of the message queue. And the best thing about this is, first of all, that it can make a lot of difference, and then that it's not very specific. It doesn't only work for gen do call, it works for your code as well, except when it does not. And that happened to me when I was writing something that looked very much like the right-hand side code. In my use case, I had two server processes that were cooperating in handling a request from the client. And obviously, if either of them would have failed, then my request would have failed as well. So I had to monitor both of them. This meant that in my receive statement, I have different references in each of the patterns, but they were all fresh and unique references, so the ref trick could have in theory applied, but the compiler wasn't smart enough to detect that and didn't apply the optimization. Next one is an extract from the OTP21 release notes. In code such as the example function that takes the tuple OK value and returns the tuple OK value, a tuple would be built. The compiler will now automatically rewrite the code to example function that takes tuple equals OK value tuple, return tuple, which will reduce code size, execution time, and remove GC pressure. Sounds logical? I think so. Actually, I always assume that this is something that the compiler did for me. That if I sprinkle the same term around in my function, the compiler will detect that, okay, this is the same thing, it's immutable, so I can just use the first instance in all the other places. Because this is kind of a thing that compilers do, isn't it? Well, apparently not ERC, at least not until last year. But ultimately, the goal for this talk is obviously to prove that man can still beat the machine. We can write faster code than the compiler can. And this is an age-old race. I guess it's on since the first compiler was released. And when it comes to targeting things like x86 assembly, I guess we are lost. Humanity has lost. But maybe the BEAM is a niche technology, didn't get as much money poured on it, so we may still have a chance. Let's explore it. And I need to introduce myself at this point. I'm Daniel Szoboszlay. I work at Klarna, but I must admit that it's not very relevant for this talk because I do optimize a lot of Erlang code, but I never do it on the assembly layer. Day job is fun, but it has to be about more things like fun and profit at least. And I'm not a very active user of social media either, so I don't have a lot of handles to put on this slide. Instead, I put my picture there just to fill the void. I only mentioned my GitHub account because all the examples you will see on the slides, I publish them there so you can play with them yourselves as well. And I must tell at this point that I couldn't be standing here and giving this talk if it weren't for the excellent blog post from Björn Gustafsson on the new SSA compiler pass, and of course up is the BEAM book, most of them which are excellent resources if you want to get started with assembly programming on the BEAM. So, Useless performance optimizations on the beam. I have to start from the end and talk about the beam a bit. At least that's what I thought, but this year something very special happened on this conference. So this is the 4th time I'm attending, and in the previous 3 years, I cannot recall any assembly code. And this year, I saw at least 3 examples of snippets on the screen. So the only possible explanation, I think, is that writing beam assembly code became from some arcane art to very mainstream things in the last 12 months, which is shocking to me. Who could fully understand all those snippets on the slides? Some people. You will be bored in the next 10 minutes. And who would like me to elaborate a bit on this topic? Yeah, so my life and presentation still have some meaning. So, the Beam VM. This Beam is a register machine, which is a bit different from the stack machines that are very common in virtual machines. It means that your process has a large number of registers to store the values it operates on. They're called x0, x1, and so on. It also has a memory area. And on the memory area, it has a heap that grows from the bottom and the stack that will grow from the top. If these two things would meet in the middle, then you have to allocate more memory and garbage collect. Why do you actually need 2 kinds of memory, a stack and a heap? It all starts from the fact that the registers are fixed size. They can hold only 1 machine word each, which means you can only store them so-called immediate values, which include small integers, atoms, bits, things that fit into 1 machine word. Anything that is bigger than that is called a boxed value, and these types include list cells, tuples, maps, a lot of things. Those need to be allocated on the heap, but the pointer to these box tuples is an immediate, so you can put the pointer into the registers. And the only way to interact with the heap is via these pointers and using machine operations that will like fetch 1 value from the tuple for you. You cannot retrieve the memory address of a value on the heap and use it for calculations on the beam assembly. So we know what the heap is for, but what is the purpose of the stack? So the stack is also addressable machine word by machine word. These are the so-called Y0, Y1, Y2, and so on, Y registers. And the purpose of those is that you can move value there from the registers. And why is it important will be clear when we discuss the calling conventions on the VM. So when you call a function, you have to place the arguments in the X registers. First argument into X0, next one into X1, and so on. When the function returns, you will find the return value in X0, and all other registers will be destroyed. So if you need some value from before the function call you make, and you want to use it after that, you have to move it somewhere, and that somewhere is the stack. That's the purpose of the stack. But there are not only functions that you can call, you can also call BIFs, and BIFs are much more flexible. You can tell the BIF in which registers it finds its argument and where to put its return value. And the best thing, it won't destroy any of the other values in your registers. One more important duty of the programmer if you are writing assembly code is keeping track of how many X registers are in use. And every time when you do an operation that may result in the garbage collection running, you have to pass it as an argument for the operation. And this includes pretty much almost every operation. For example, if you want to explicitly allocate heap or stack memory, or when you are calling a BIF that may implicitly create a term on the heap. And remember, even big integers are box types, so it includes simple arithmetic operations as well. Or when the process may get scheduled out, which can happen on the function calls, certain BIF calls, or when you want to send the message. Great. How does the instruction set look like? There are a total of 168 opcodes, and I don't want to show all of them for you. I just wanted to give you a big picture of the most frequent ones. And there it is, this nice tech cloud. I generated it from the Amnesia source code from OTP 22 RC1, which is the version of the compiler that I use for all these examples. And I think amnesia is quite representative of how an Erlang application used in a control plane may look like. If you would compile, I don't know, a JSON parsing library, that would be probably a bit different. But when it comes to amnesia, it compiles to 62,000 opcodes in total, and there are 78 different ones. By very far, the most common one is move. Move is for moving values between the registers. 34% of all the opcodes are moves. The second most frequent one is call ext, which is calling an external function. Then comes get tuple element and put tuple 2. Both of them are opcodes for working with tuples. Then test heap, which is to ensure you have enough heap memory available for the next term you want to put there. And there were 9 more opcodes that had more than 1% share, and then came the long tail of the remaining 70, I don't know how many. And at first, this overwhelming use of move was a bit strange to me, so you have to ask questions of yourself that, is my Erlang code that slow because it spends 1/3 of its time just moving data in memory instead of processing it? And probably yes and no. These things can be quite fast, so but indeed you need a lot of moves, and that's because of the call conventions. Before each function call, you have to save all the data to the stack that you want to use later, move in the values into the arguments into the proper X registers, then do the function call, save the result, and do it again. A lot of moves indeed. But the other important thing to learn from this bird's eye view of the instruction set is that it's actually Erlang all the way down. So it's not like when you're compiling your code to machine code. Like you may start from a language like Rust that has very fancy types. Once you go to machine code or the equivalent of it, some assembly code, then those types disappear. You will only see a bunch of integers, and any value you have, you can use for any purpose because everything is an integer. You can use it for arithmetics, you can use it for pointers, offset to pointers, instructions, anything. Not with the Erlang VM. You cannot do very dirty things like put on a heap a tuple and then later on try to use that memory as a list. It won't work. Once a tuple, it's always a tuple. You can only access that memory with opcodes that are specific to tuples and designed to work with tuples, which I think is a great thing as a property for a language. But when you are in my shoes and you try to hack the system and cut corners and speed things up, then we will have harder times, I think. Let's see some very specific example. It will be simpler than the previous snippets you could see, the hello world in BEAM assembly, and of course in Erlang as well. The first thing to note is that the assembly language is basically a sequence of Erlang terms, and it's also a very verbose format. For example, the x0 register here is referred to as the x0 tuple. Or whenever you see an atom or other Erlang term, you have to wrap it into a tuple that holds some type information. And this code is very easy to parse by machine, but quite hard for a human being to write. You can trust me on this one. Now, the actual function starts with this function tuple that will tell you the name of the function, the arity, and the final value 2 is the entry point. It's a reference to a label. Labels are quite common things in assembly code, and these are the points where you can jump to in the program. So let's start reading from label 2. First operation is a move. We move the value we want to print into x0 and then do call ext only, which is a tail recursive external function call to io_put_1. Remember the call conventions. The one and only argument needs to be in x0, and this is exactly what we did in the previous step. It couldn't really be simpler than this. Except we also have this label one and this func_info. What are those? Well, func_info is a dual purpose opcode. If you would actually execute it, it would raise a function close error. Why do you need a function close error for a zero arity function? And even if you want a function close error to be generated, why would you put it into the beginning of the function? Why not at the end, like a sort of a close after the last close thing? That's because it has a second use when you are making local function calls to hello world. Those operations won't tell you call the hello world function, they will refer to it as label. So they will say call the function at label 2. But sometimes the VM needs to know what function label 2 corresponds to. So there the convention is that it can go back and see one instruction before the label, and it should find the func info there and know the name of the function from there. So now you are all prepared to actually see some performance optimizations. I will start with the case study of adding the ref trick to a place where the compiler didn't find it eligible, and this will be a very, very low-hanging fruit, trust me. So my demo code here is that I have two processes. I place a monitor on both of them, send a message to both of them, then go into a receive and either get a response from one of them or one of the monitors will send me a down message. And just from the four initial lines, I got this much longer body of assembly code generated. Let's quickly see what it is. First, we allocate 4 words on the stack for values we want to survive function calls. Then we move there the 2 arguments because we will need them later, the 2 PIDs. Then we start preparing for calling Erlang monitor. So we arrange the arguments on the X registers, we do the call, we save the value, and then we start preparing for calling the second Erlang monitor. And once we are here and done with that, we build up the message tuple that we will send eventually to PID 1, and then we do it again to send it to PID 2. From the receive statement, this even longer set of instructions are generated. I won't go into too much details here. I just want to show you how the processing of the mailbox look like. So everything starts with loopback, which says, fetch me the next message from the message queue into the X0 register. And it also has this F9 thing. What is that? That's a reference to label 9, and it says what to do when the operation fails. This is a common pattern in assembly. You can see, for example, also in the test operations that we provide some F8, F6, such a failure label. So if this test would succeed, we would continue with the next line. Otherwise, we would jump to the failure label. So fetching a message from the message queue can only fail if there are no more messages. Then we go down to the bottommost instruction under label 9, wait for the next message. When it arrives, we go back and try again. And eventually we will find a matching message, and we arrive to remove message. This is the end of the processing of the message box. We remove the message we found. If the message doesn't match, we will end up under label 8 and do this loopback call, going back once again to the beginning of this loop. And to use the ref trick, we only need to insert 2 more opcodes. Before the first time we call the monitor, we do a receive mark, saving the position of the last message in the message queue. And then before we enter into this loopback loop, we receive set this internal pointer of current message to that position that we just saved. Problem solved. But if you look carefully, you can find a few more places where you can optimize things a bit. One is that the 2 messages that we want to send. Actually, they are identical messages, yet the compiler builds up the same tuple twice and it allocates space for 2 tuples on the heap. It doesn't seem reasonable. Why didn't it recognize that we have the same thing? And my guess is because it contains self, and the compiler doesn't probably know that self is a pure function. It will always return the same value and won't have any side effects, so we could just simply cache the result of it and reuse it instead of calling it multiple times. The other will be a bit more, so we can eliminate those instructions. The other will be a bit more tricky. It's the code that is generated from pattern matching on the 2 dumb messages. And you can see that ERLC is quite smart here. So it figures out that the 2 dumb messages are almost identical, so it generates a single code for most of the pattern matching. First, it already knows that it's a tuple, so it will fetch the values, elements from the tuple into registers, and then verifies that the down and process atoms are in place, and then it only has to decide whether it's one of the 2 concrete monitor messages. So first checks whether PID1 and MON1 are in the message, and if yes, we found a match. If not, we try again and pattern match against P2 and Mon2. And this could be a bit more optimal by swapping the order of the test and starting with pattern matching on the monitors. Why? Because if because the monitors we know are unique values. So if we see monitor 1 in the message, then even if we don't see PID1 there, it cannot be the second monitor because that has a different monitor there. This is not true for the PIDs. PIDs were arguments we receive, so they can in theory be the same thing. So just by seeing PID1 in the message doesn't mean there cannot be PID2 as well in the same position. So this is something we could optimize a bit. I admit that these last two things probably didn't matter at all, but I'm still proud of them because it means I can write faster code than the compiler. But when I measure the times, I'm sure that it's 100% due to just using the ref trick. And this is what it can do for you. The execution time is as the function of the number of messages in the message box. The original version is quite linear, and one using the ref trick is almost constant. Big win. Next case study. We will try to do something more challenging here. Eliminating redundant tests on recursion. And the idea here is that when you do a function call with a function with multiple clauses, first you will have to probably do a bunch of tests to figure out which clause to execute. But if you are calling from within the same module, from a context where you know something about the arguments, then you may have enough information to not perform all the tests. So you may know that this clause cannot match. And we could do that if a function would have multiple entry points. So we don't have to necessarily jump to the first entry point, do we? It's just a label. Why cannot we just jump into the middle of the function and start from there? So the demo code here is this one, which is looking for the greatest common divisor of two, in our case, non-negative integers. So the first clause is for putting the arguments in the correct order. The first one should be bigger than the second one. The second clause is the stop condition. When the smaller one is 0, then we find the greatest common divisor. And the third one is where we will loop, take the remainder of the arguments and continue. And the code that is generated by erlc from this function is quite straightforward compilation of this thing. What we have under label 2 is the same thing that we have in the first clause. We swap the arguments when necessary, and we will do a call, only a tail recursive local function call back to label 2, the entry point of this function. Otherwise, we continue and check whether we have reached the stop condition, and if not, we will continue with the third clause. And at the end of the third clause, we will do a recursion, once again going back to label 2. But these are not optimal. Once we swap the arguments, we know that we don't have to go back to label 2 and swap them again. We know they are in the correct order. We can continue from label 3. And the same is true for this recursion. We can skip checking the order of the arguments. So this is one thing, but there are also a few minor things here that we could optimize, like this guard test that the A is greater than equal than 0 is duplicated. So if we fail here, then we go to label 4, when we execute the same test again. So it doesn't make sense. We should from here immediately go to label 1, which is the function clause. And there's one more little inefficiency here, and this is the rem BIF, which we tell that put the return value into x0 register, and then we will have to basically swap x0 and x1 immediately, and that takes 3 operations. If we would have put it into any other register, then it would be only 2. So we could eliminate these things. And my dream function would be something like this, which is still very literal translation of the original one. So we first test the order of the arguments, and if we have had to swap them, then we do a recursive call and go to label 4. We don't repeat this test anymore. Then we check that the arguments are both non-negative, and if they are, then we go into a very tight loop where we only test reaching the stop condition, and when we do a recursion, we go back to disk label. This is nice. The problem, it won't compile, and it actually crashes in a point when I think erlc tries to do that code elimination thing, and then it has some built-in assumptions of a function having one entry point. So it's not nice, but we can have some workarounds until the beam gets fixed. One would be to split it into multiple functions and introduce helper functions at label 4 and label 6, which would only result in the traces, if you would trace this module, to be a bit strange because they would report different functions to be called on recursions. And you can argue that this is some optimization that I don't need to do on the assembly level layer. This can be done on the Erlang layer. Yes, in this case of the simple function, it's true, but it would be nice if the compiler could do this for me for very large and very complex functions, and I wouldn't have to come up with totally totally unnameable helper functions, because naming things is very hard. The other option would be to, instead of colonless, use just jumps. And that works, so we will just jump around in the code and not do any recursions. This is a bit cheating, because then you cannot, you won't, of course, get the proper traces if you are happening to be tracing, and you will also not bump the reduction counters, so you would hog the CPU if you have to make a lot of recursions. But you can do that if you want to speed up things and cheat a little bit in your assembly code. Third option is to try to get the best of both worlds and do a loop, or in this case, recursion unrolling. So unroll this last loop a couple of times, and maybe after every 10th one, just go back to the initial label with a recursive call. That would eliminate 90% of the overhead. So how do these different variants perform? The green line is the stock Erlang compiled version, and I was expecting the jumping code to be the fastest. The helper function should be a bit slower, because probably doing function calls is less, it's more work than just jumping. But they turned out to be equally fast within measurement error. Unrolling was nicely in between the lines, just as you would expect. And finally, I put there with dotted lines the erlc compiled version, but this time with inlining and loop unrolling enabled, as it was suggested by Richard Carson. And I was not expecting that to speed up things much, because loop unrolling wouldn't eliminate an unnecessary test probably, but in fact it made things even slower than the stock versions. I don't know why. Maybe because code grew too much and we got more cache misses. I can't explain it exactly. Yeah, these were the detailed use cases, but I can give you a few more assorted ITs where you won't have to read more assembly code. Just listen to me. I had, of course, a bunch of wild ideas that I tried and they didn't work. You can, when you think about programming in the assembly layer and speeding up things, the first thing you would probably want to try is making destructive updates of terms. And that is indeed possible with assembly instructions. There are opcodes for doing destructive updates on tuples, but they are very limited. Besides the fact that you can very easily crash and segfold an emulator, you need to supply the position of the element you want to update as a hard-coded value. It cannot come from a parameter and cannot come from a register. So it means that I couldn't come up with any practical algorithm that could exploit this functionality in this present form. Then you may think about using some custom call conventions, like let's return 2 values from a function, because there are a lot more registers. I can put there as many as I want. I guess that would work, but the compiler wouldn't compile my code, because it has very strict checks on which registers you use, so it catches me. Maybe if I would manually compile it into a BEAM file, then it would work, but I didn't go that far down. And sometimes you run into very strange limitations, like jumping to an earlier label. That sounds totally reasonable, isn't it? But it happens to crash the OTP21 compiler. So my examples only work with OTP22. But you can still have a chance to find a lot of places to get performance gains or do other dirty tricks, like the fact that you can go through the message queue of your process and react on the messages without removing them from the message queue is one such thing. Using jumps instead of calls to avoid bumping the reduction counter can be one more. And there are a bunch of things that I noticed in the code generated by the compiler that should be or could be improved, like detecting the creation of identical terms even if they contain things like self, or when the same guard is mentioned on multiple function clauses, then there's really no reason to evaluate it multiple times. Or when the return value of the BIF was not placed into the optimal register, it had to move immediately. They don't really make sense. Or if you, in your Erlang code, write fun in the format of fun name /arity, then that the resulting fun object will not contain that function. The compiler will introduce you a simple wrapper function around the function you mentioned there, and you will get that one. I don't know why. It bothers me because then I cannot use funcinfo calls to figure out the name of the function. I will always get back this garbage generated fun name instead. And I think there would be a lot of nice possibilities in doing some code factoring, which means unifying similar code paths. Because at the assembly layer, even very simple things like return the error reason tuple, this can take 4 instructions or so. And if you do it from multiple places in a function, it may make sense to create a label, put this code under that, expecting that x0 will always contain the reason, and then just jump to there. Imagine if you could do that from all the places in your function, it could reduce the code size a bit. If you could do this from all the functions in your module, that could be an even bigger win. That could be relevant for embedded systems, for example. You can't do the latter at the moment because the compiler will also check that you don't jump between code that belongs to different functions. Your hands are tied a bit if you want to hack on the assembly layer. So finally, useless performance optimizations on the Beam. Why I do things that these optimizations are useless? Mostly because writing manually assembly code is very, very impractical. My biggest reason for calling it impractical is that because you cannot embed assembly code into an Erlang code. Like in most C compilers, you can do that within your C function, within code, you have a little assembly layer and do 1 or 2 tricks for the really performance critical parts. I can't do that with Erlang. I cannot like insert my these ref tricks to the place where the compiler doesn't recognize it for me. So I either rewrite my entire module in assembly or I don't optimize it. I guess everybody would go with not optimizing it. And the assembler itself is quite unfriendly. You have to write a very verbose syntax. You cannot use named values for labels. You have to use integers, so it's hard to read. You have to write a lot of boilerplate, like the module info functions. And the worst thing is that it's really, really not meant to be a human interface. If you make a typo, the most common result is that the compiler will just crash and you get a long stack trace with no way references to the original point in the code that went wrong. So it's not nice. And the ultimate reason is if that you really need so much performance critical tuning, then writing an if would be probably have 10 times or 100 times more return on investment. Less effort, more gains. But what are the actual benefits? Why do I think that we still have to learn about this layer. First of all, if you know the limitations of the compiler, then it can help you become a better programmer. You won't have unrealistic expectations like I used to have with RefTrick, or you can actually adopt a coding style that you know the compiler will be able to optimize. The other thing is that if you spot inefficiencies, then you can actually try and improve the compiler. And I think this is a very exciting challenge. There are definitely low-hanging fruits, as I've hopefully shown you today. So the next step is not necessarily to write a JIT compiler. You have to start from much smaller steps and improve things yet. And I think it has the additional beauty that it's a relatively flexible interface. You can even add new opcodes to the language, which happened in OTP 22, as long as you keep supporting the old ones. And being a machine-to-machine thing, you don't have to care that much about developer ergonomics, I think, which probably are a big reason for changes to the real programming APIs are slow because everybody has an opinion on them. And here probably less people would be worried. So here's my call to action for you. Take your time sometimes and try to compile your modules to assembly. Inspect the code, understand what it does, try to spot inefficiencies, and once you have some, try to fix them in the compiler so it will generate better code. Because the OTP team does wonders with the VM, but they are just so many people with so much resources. I think the community should really help. And then if you do that, then hopefully it will be no longer just fun and fun, but it will be fun and profit for all of us if we get a faster VM. Thank you very much. And
thank you very much, Daniel. A brave talk with the entirety of the OTP team here watching. Are there any questions? Yes. There they come.
Okay, I do have a small list here.
Okay.
Okay. Did you try to reuse the self that is create a middle term that you sent in the two cents and see if that helped?
Yeah, I did that optimization as well. But to be honest, so if you change very, very little things, then
I guess you couldn't
really measure the difference.
It didn't create two terms at least.
My version didn't create two terms, yes. So I didn't write a test case where I would have copied this code maybe 1,000,000 times and see whether that have a measurable effect. But with only one duplication of the code, I couldn't measure it. And the thing is that I tried to do my best to make accurate runtime measurements, but still there's a lot of noise in this, probably because I'm on top of the VM that does a lot of other things, plus the operating system and whatnot, and I'm trying to measure a few nanoseconds of difference.
Okay.
I couldn't measure it.
I agree with you that you read the BEAM code and then you try to figure out how to trick the compiler into doing the right thing. That's often fruitful. And did you know that in 22 there are a lot of these type optimizations to not check types on function entry if you do recursive calls and so on? They have been introduced in 22.
Yeah, what I heard from Klarna is that it's done on the return values, but I haven't compared the 21 and 22 compilers. But those examples were generated with the 22 RC1 compiler, and it couldn't find those scenarios that I try to optimize. But the compiler currently is also limited by the fact that it needs to stick to one entry point per function, and this function being exported cannot rely on the fact that it can need to work only a subset of the possible types. It's exported. It needs to rely on needs to work on any possible argument. So maybe if it would be an internal function, then it could do better. But my point was that if we trick the system and create multiple entry points, then we can even speed up these external exported functions.
Okay. Last point, that fun name arity that became a function in between. Okay, did you know if you use an exported instance fun module colon name dash arity, that becomes a call to an
Yeah,
function entry
that's a
point
completely
instead?
different thing, as far as I can tell.
Yes, but it would do what you wanted, I think.
Yes, but then you would have to export the function, and I don't have
Unfortunately.
any problem with exporting internally used functions. I think we do it a lot of the times. Like all the behaviors basically ask us to export internal functions. You don't want anybody to handle call directly in the module except for Gen server. But I know people sitting around me in my office that who think that you shouldn't export internal functions because that breaks the encapsulation of the code, and then people may have the idea of calling that, and they want a nice interface for the module that only exports what should be visible.
Very, very good talk. I like it.
Thank you.
Few things, yeah, and like your suggestion to contribute to the compiler, that's a very good idea. We would like more contribution to the compiler. It's more optimizations, and a few comments about wrappers for funds.
Yeah.
I think we have them because to support native code, it needs a wrapper function for some reason.
Okay,
And native code also doesn't like jumps from one function into another function. I actually did that optimization early, but then Hype that told me that was unclean and it was very difficult to support. So now to make it cleaner for that.
Okay, this is interesting addition. I didn't try with Hype, to be honest. I should have now. I say to see what works with Hype and what not. But maybe because now we have Diverge and OTP22 doesn't fully support Hype, we could use these optimizations unless you are running in Hype enabled mode.
We can't know whether it will be used. People can compile from a BEAM file later convert it to native code. So we can't do any special.
I know, but the OTP22 release note states that there are new opcodes that break Hype, and you have to specially enable some compiler flag if you want to get code that can be reliably used by Hype. So maybe this would enable us to use these not Hype friendly tricks.
Yes, in a future release,
Yeah.
we might do that.
Yeah, I was just curious about one of your first slides. You say that you can't trace beefs.
I said that you can't trace beefs. Yeah, but you cannot trace things like the plus operator, I think. So, yeah, it is a function, but like, where do I have a beef here? Like, if here we have a beef called to RAM, and you cannot trace this RAM. If you would write call Erlang :RAM, that function explicitly, then it would be a function call, I think, and then you could trace it. But normally you cannot trace these operators.
Yeah, you cannot trace guard beefs. And operators are guard beefs. They are even if they're not in guard context.
Even them.
It's the same instruction. Okay. All right. Thank you.
One more question. I think the mic is off.
So, yeah, it is. Two comments. A lot of the things that you try to optimize would have been called by the Hype compiler process. A very useful project would be to go into the Hype compiler and look at the compiler optimization process. And now, since Beam code is also on SSA form, you can more or less take the Hype compilation optimizations and just apply them to Beam code instead. I think that would be a very nice exercise.
It would be. May I ask you that why didn't you do this at the time when you were working on Hype? So you can definitely do these optimizations on the original representation.
We did it in Hype because then we become faster than Beam.
Oh, okay. So this was your secret sauce that you actually optimize better the emulatable part of the code, not the actual machine code. Makes sense.
Second suggestion, the ref trick.
Yeah.
Exactly the stuff that we wanted to achieve with ref trick. I suspect that the compiler data flow analysis that is applied to find ref trick can be easily extended to your use case.
Yes.
That would save a lot of problems in the real world. Yes.
Yeah. I agree. I just wanted to show that right now it doesn't do that. So
All right, let's thank Daniel again.